the second generation of John Seminar started with Raka, one before, but he unfortunately died young, as you know. And this seminar is alive until today. It lasted since probably 66 until today, that is now John also by Jerusalem, and it takes place in Neve Shalom, as some of you know. So he is also the... We have 3 talks, and the first will be Harald Fritzsch from Munich, and he will talk about fundamental constants. Are they constants?
Well, I don't need this for the time being. Yeah, I'm very glad to be here in honor of Yuval. First time, I must say, I met him at the duality meeting in 1971. You still remember that meeting, I guess. Important meeting. And I arrived late in the evening, and Murray Gell-Mann was in the reception, which I knew where I was going to. And when he saw me coming in, he was standing there with some politicians and with Yuval, and Murray came to me, embraced me, and said, "Welcome to occupied Palestine." I was shocked by it. He was shocked. The politicians were thinking, what kind of crazy guy is coming here? But that was Murray Gell-Mann. Unfortunately, he's not here today. Since then, I met him quite often. Once, I remember at the Minerva meeting in Ein Gedi we had at the Dead Sea, and Yuval at that point came with me to the end of a canyon, and he showed me in the end of the 40s he was stationed there with his soldiers with the machine guns at the end of the Ein Gedi canyon. It was interesting for me to see it. Later on, when he was member of the Knesset, he invited me to have lunch in the Knesset, and we had many discussions with many politicians there. And once Yuval got a honorary degree in Germany, in Clausthal in Germany. Maybe Mr. Hale was also there, I forgot. And on the evening before, I was supposed to have dinner in a private home near Clausthal, and I drove there during the day. But it turned out there was too heavy traffic. I mean, the freeway was partially blocked, and I couldn't make it in time. But I heard in the radio that the freeway from Frankfurt was also having trouble, and I assumed that Yuval would not arrive just as well as me in Clausthal in the right time. But I was wrong. Yuval, being at that time minister, he was accompanied by a German police car, and they decided to leave the freeway as it is and go on the parking lane of the freeway, which is forbidden to drive, and drove him along, and so he came right at dinner time into Clausthal. I was wrong. And the next day he got his degree, and I had to give I had the honor of giving the laudatio. And then it turned out we had troubles in Clausthal because the Arab students decided to have a demonstration against him. And so there were more than 150 policemen from Germany coming to protect us. And then the demonstration came, consisting of 3 Arab students, 1 female student, 3 of them. It was a very peaceful event. And after the demonstration, we decided, I talked to Yuval, we decided to invite the 3 students even for lunch, and they came gladly, and there was no problem at all. So there are all these things which happen with Yuval. And, but I'm going to speak about something which I got interested in already about 2 years ago, and it has to do with fundamental constants. And also we'll speak later on about the time variation, which is measured in Munich right now in an interesting experiment, which I will discuss. What are fundamental constants? I must say, people working on particle physics like me, nobody has an idea. We still don't know where constants like alpha are coming from. We are dealing with the local laws of nature most of the time, but the fundamental constants are probably somehow related to the boundary conditions of the universe, in other words, to the Big Bang. And we still don't know how to look at it in the right way. And so what are these constants? My friend Murray Gell-Mann claims some of the constants, at least, could be cosmic accidents, and I will talk about it later again. Some of them could be determined by dynamics which we still don't understand, and some of them might even be changing in time. And I discuss it later. But it could well be that part of the constants are somehow created in the Big Bang. In other words, if you recreate the Big Bang, if you do it again, then you get different constants. And that might well be the case, like constants like the electron mass. Well, what are really natural constants? They express at the same time our greatest knowledge and also our greatest ignorance. We still don't know, are they really completely constant? It also turns out that the existence of our life on Earth depends on a specific choice of these constants. And if alpha would have a different value, it wouldn't work like this. Albert Einstein, which I read recently, I got a letter, I was reading through some papers, and accidentally I found that interesting letter, which Einstein wrote in 1948 to a woman in Croatia. He wrote dimension in German, but I translated it, dimensionless constants in the laws of nature, which from the purely logical point of view can just have very different values, should not exist. To me, with my trust in God, this appears to be evident, but there will be few who are of the same opinion. And also, I must say, I'm also one of the few. I'm also against Einstein in that way. The fine structure constant is a beautiful example. It has a relationship to my home place in Munich, but I got my job eventually from Mr. Sommerfeld in Munich. And Sommerfeld was a long-time professor in Munich, as you know. And already in the year 1916, he introduced the fine structure constant. It's E squared over h bar c. It's a very nice combination. Combines electricity, quantum mechanics, and special relativity, making it in one dimensionless constant. Sommerfeld was a bit surprised why that constant, the inverse of the constant, is close to 137. For a while he thought it's an integer, but it turned out it was not an integer. A lot of philosophy went with it. I don't want to mention this. I just mentioned that Pauli in 1958, when he already at the age of 57, he died unfortunately much too early. Pauli had the joke when he checked into the hospital, and you know he's going to die in that hospital, in the Zurich Kantonsspital. He told the doctor in charge, put me up in room 137, and he was put up there. Vicky Weisskopf, when he said goodbye to him, he closed the door and he noticed Pauli died in the room 137. Leon Lederman, even today, lives at 137 Eola Road, Illinois, but this is not an accident. He, as a director of Fermilab, he simply decided this is 137, and that's the end of it. Dick Feynman, which I was together with him for quite a number of years in Caltech. We often had lunch, and once he told me at lunch, you know, you are a theoretician, and we all should write on our blackboards 137 dash how little we know. We still don't understand 137. When I went back from that lunch to my office, I checked in Feynman's office, I couldn't find anything. So I wrote on his blackboard, 137, how little Feynman knows. Then he came to my office 1 hour later, looked at my blackboard, nothing was written. He wrote down 137, how little Fritzsch knows. And I kept this notice, I kept on my blackboard for the rest of my time at Caltech. Whenever Murray Gell-Mann came in, he said, why don't you erase this crazy statement of Feynman? Feynman doesn't understand anything, not even about 137. But I kept insisting I keep it on. I should have kept it and take the blackboard with me eventually, but I couldn't. Werner Heisenberg even wrote a paper in the 37 where alpha is this value. It's rather close to 137. Heisenberg would not be very proud of that paper today. But when I was a graduate student in 1971, part of the time I was at CERN, and there happened to be an interesting colloquium by Armand Wühler, a mathematician from Zurich. And he had this formula, which even today works very precisely, up to 1 part in a million. And this was not an artificial invention of Wühler, Wheeler got that number by comparing the ratio of two group spaces. Don't ask me which groups it are. Probably it doesn't make any deep sense anymore. But I mentioned that equation, nevertheless, sometimes to string people, because the people working on string theory are like to derive alpha, and perhaps they should look at this original argument of Wheeler. Wheeler got very famous with this formula. It was written in the New York Times. He was invited to the Institute of Advanced Study in Princeton, and working with Freeman Dyson and things like that. It was interesting. Yeah. Quantum electrodynamics, which is dictated by alpha, is of course a very successful theory, much more successful than anybody was thinking before. People who had invented the theory, like Pauli and Heisenberg, and to some extent Feynman, did never think it would work to such a high precision. But it seems to do. And today the value is written here. Unfortunately, part of my transference I have German statements, but forget about it. I couldn't change it so easily into English. This is inverse alpha. And so what we do with alpha? Well, first, one thing I should mention. In quantum field theory, as you well know, the coupling constant is not a big deal. It's a function of the energy scale, as was also pointed out by Ken Wilson to some extent. And it's a partial screening of the Baire chart which takes place. And the effective value of the coupling constant, depending on the energy scale, is a function of the logarithm of Q squared. And if you do that, and compare it, let's say, to the values measured at lab, here, at high energies, you have to introduce all the other fermions, quarks, W boson, and the change of alpha is changing on the number of particles available. Then at 200 GeV, the highest value is reached at lab. It's about 127. A rather precise value is obtained at the inverse, at the coupling constant at the mass of the Z boson, where it's 127.8. And so the question is whether, if Pauli would die today, you might decide also to go into the room 127 and 137. In quantum electrodynamics, of course, it's coming from the virtual pairs surrounding it. And so it's the effective value is going up here. And at the lab value, at MZ, it's reaching this value of 127.8. And the other constants we have in physics are related, many of them, to strong interaction physics. Here's a picture of the proton, actually taken out of a Scientific American article. And the inverse of the confinement radius is called lambda, the critical energy scale of QCD. And if we today would write the mass of the nucleon, it is something proportional to lambda, which is a dominating term, and then some small corrections proportional to the fermion masses with certain constants. And these constants, in principle, we can calculate. As a joke, sort of, I have written down here the mass of the nucleon with very high precision, and here I have put in the various values coming from the various contributions, just as a guess. Nobody can work it out so precisely today. But you see the electromagnetic term is about 2 MeV, and the pure QCD term is about 815 MeV. And that's a picture of the nucleon mass. Many other constants we have in particle physics, and and that is really the dark corner of high energy physics today. Nobody still has an idea where the fermion masses, the electron mass, and all the other masses are coming from. Here, the fermion mass in the standard model is just proportional to the mass of the given by the virtual Higgs particle. Whether that picture is correct, we still don't know. But we know if it's correct, the energy scale is 246 GeV. That's not calculated. That's coming from the measurement of the Fermi constant. And that's it. Many years ago, I was supposed to give a talk at the meeting of the 60th birthday of Murray. Maybe Yuval was always there. I think you were there also. And he had a meeting going on. The day before, I asked him, what should I talk about tomorrow? Then Murray looked at me, and then he was smiling and said, Well, it would be good if you say something about the electron mass. I was looking at him and said, what could I say? Nobody, you don't know, I don't know, nobody knows anything about the electron mass. Well, think about it. So I went back to my office, I talked to Yuval Telekti, and he said, don't worry, just give the electron mass in terms of funny units, like gram, kilogram, and pounds, or whatever. So I was sitting down, making a little table, and then I made an interesting discovery, which had some consequences afterwards. Because I found out if we express the electron mass in terms of, in the United States, this is the usual unit, American pounds is here. It's exactly an integer, 2.000. The first departure is only very later on. Integer times 10 to the minus 30 pounds. Even today, when I have forgotten what a pound is, I take out my CERN booklet, I mean the particle physics booklet, look out, take the mass of the electron in kilogram, and then convert it with my ratio, and I have everything in pound. And I mentioned this as a joke in my talk, and I didn't know that Nick Samios was in my talk. Of course, I knew him, but I didn't know he took a note of it. And the weekend later, he had lunch with a famous friend of him. He was a senator of Massachusetts, Sam Nunn. And Sam Nunn took a note of what Samios told him. And 2 days later, they had a meeting in the American Senate about converting to European units. And then Sam Nunn raised his hand and said, there was a European physicist who has found this relation, and I think we should base ourselves on basic particle physics, and so we should keep the American pound and not introducing the kilogram. That was a dangerous event, because without that argument, Sam Nunn might have not gotten through, and the America would have had the kilogram right now, but they don't. And because of that funny accident. It's my fault, I must say, but I shouldn't have said it in my talk. That's the way it came, very strange. But when we look at the constants in the if you are a solid state physicist, you don't want to hear about top quarks and stuff like that. But the constants for stable matter, which is interesting for you, are still given by basically 5 or 6, or rather 6 constants. The electron mass, the up quark mass, the down quark mass, which they determine the nucleon mass. The strange quark mass also, because the strange quark also plays a certain role in the nucleon mass. It's about 50 to 100 MeV, it's quite a large effect. And the QCD lambda. These constants are enough for you to determine our world, that's all. And only if you are interested in particle physics, you go to the next layer of constants, and that's given here. It's not even the last one, which are about 17 constants, or 18 coming in. In the center, I have placed the first constant ever introduced by Isaac Newton, gravity constant. Then alpha, the strong interaction analog of alpha, or lambda, the weak interaction analog. Then out here, I have all the fermion masses, the electron mass and whatever. You see, neutrinos are still massless. I still didn't include the neutrinos. And then here, certain flavor mixing parameters. The mass of the Higgs boson, if it exists, we still don't know, and the mass of the W boson. Quite a lot of constants we are dealing with. Including neutrinos, you have more than 26 constants. It's a large number. Some of these constants might actually be no constant, but determined by the other constants. For example, I believe that the flavor mixing parameters are just given by ratios of square roots of mass eigenvalues. And that works extremely well even today, up to something like 3–4%. And if you have relations like this, the number of parameters in the standard model, which is right now 18, would go down to 14. It's still a large number, but to go further is very hard. But now comes another thing. And this is unfortunately one of the 1 or 2 German transparencies I have. I couldn't change easily. A time variation of natural constants. It was observed in a big experiment around since the year 2000 or so, looking at distant quasars, and it seems to be that alpha is changing a little bit in time. It's really a very important discovery if it's really found out that it is that way. It was an experiment, which I have here on the next, I think, run by a group from Australia, Mr. Webb, by Art Wolf and collaborators from the US and some people from England. And they looked at the fine structure of atoms in distant quasars, iron, nickel, magnesium, and things like that. Some of the quasars were even 11 billion years back in time. I mean, really almost come close to the Big Bang. And this is the value, not the published value, but the real value they published last year or 1.5 years ago again. This is a change. 2 years at the place of 10 to minus 5. That means alpha has changed. The early on alpha was a bit different from the one today. And if you do a linear approximation, it's about 1 or 1.2 times 10 to minus 15 per year. Very small change. And I will come back to the change in a few minutes. Here are the data. The data look not so terribly impressive, but still it's interesting to worry about it. And this plot is based on age of the universe of 13.9 years. It depends on a little bit on the age of the universe. Doesn't matter too much. And now about this, I have to mention something else. Some of the nuclear people among you might know the so-called Oklo phenomenon. What is Oklo? It's a natural reactor which produced by nature, there were no humans around at that time, of about 2 billion years ago, near the river Oklo in Gabon in West Africa. Why could at that time be a natural reactor? There are several places on Earth, also in America and in Siberia, where natural reactors occurred. Well, accidentally you had a high concentration of uranium, and at that time the uranium-235 was about 3% 2 billion years ago. Today it's only 0.7% because of decay. So it's much higher. There were accidentally a low concentration of neutron absorbers, was a critical size, and also even a moderator was around, provided mostly by the water in Gabon. And it's interesting that natural reactor worked for about 100 million years. In Germany, reactors are working now for 30 years, and the government is closing it down. The present government, I hope the next government next year is going to change that again. But they're right now closing it down after 30 years, but it operated for 100 million years. I wonder what the Green Party was doing 2 billion years ago. They were sleeping, I guess, not closing down the Oklo reactor. Here's the ocean, here's Oklo. And the time scale was mentioned about 2 billion years. And now what's interesting about Oklo is the following. It was pointed out by a Russian physicist called Fritzsch. He was even invited to Harvard and spent then, but then in the meantime he died rather early at the age of about 50. Very strange thing at Harvard. But Fritzsch pointed out the following. It was later on by Damour and Freeman Dyson in '96, so about 8-9 years ago. They worried about it again. Looking at samarium and various other elements. Now, samarium is particularly interesting. Why? Because in samarium, if you absorb a neutron, it goes to samarium 150 emitting a gamma ray. It's a normal nuclear reaction. However, it turns out this cross-section is particularly large because there is a nuclear resonance close by. And it's just above threshold at resonance. It's only about 0.0973 electron volt above threshold. And that makes this cross-section also big. And the point is then the following, pointed out by Fritzsch, later on by Dyson Damour again, that you could say something about time variation of alpha through this observation of the cross-section. Why? Well, if you take a simple nuclear Hamiltonian, I have an electromagnetic contribution, which normally can be easily worked out, just E squared times the inverse radii of the various nucleons. And that way, if in a bit of Weizsäcker approximation, you get a very similar result, but this was a calculation. The change of alpha times the resonance change of alpha, the differential change, is less than 1.09 or whatever MeV. And therefore, you can then say something about the change of alpha at Oklo time minus alpha now. And this relative change is less than 0.07. And it was then from that calculated by Dyson and Damour in particular, that the change of alpha should be less than 10 to the minus 16, perhaps even 10 to the minus 17. And that is interesting because, I said before, these astrophysics measurements set a change of 1.2 times 10 to the minus 15 that would be excluded by that number. And the question is this really correct? I tend to believe this is not correct. Why? Because the Oklo constraint is questionable, which was also pointed out by Dyson and Damour, if you also have other changes coming in. For example, changes of lambda. And why could that be? Well, again, we seem to have a contradiction. The linear approximation gives this result, the Oklo gives this result, and they disagree. Of course, one is can easily be understood if the Oklo constraint is invalid by a nuclear change. There could also be other effects which I'm not mentioning right now. Let's forget about this right now. And before I discuss it again, bring it up, let me also mention some history. Let me make some historical remarks. In the 30s, Dirac and also Milne discussed the time dependence of fundamental constants, in particular the gravity constant. But Pascal Jordan, actually Gamow didn't like what Dirac was writing. It turns out Dirac wrote his paper, his famous paper by now, at the time when he, immediately after he got married, he went out with his wife to Italy to a nice trip, and then he worked out that paper. And then Gamow wrote in his paper, that's what physicists do when they get married. They write crazy papers. That's, what can you do? Pascal Jordan discussed other constants. Leo Landau in the 50s discussed a time variation of alpha in connection to renormalization. Well, alpha, as you know, is E squared over h bar c. And for me, as a particle physicist, h bar and c are holy quantities. Usually I put them equal to 1. So you could not discuss a possible time dependence of h bar and c. But I must say, right now there are lots of papers written by astronomers discussing a time variation of the speed of light. I don't know what they are doing, because if c would depend on time, Albert Einstein would have a very bad time, and relativity couldn't really work anymore. At least not, it would be broken by some small terms. I don't know what to do with that. So for me, h bar and c, I don't want to touch. Also h bar, if h bar depends on time, Max Planck is going to rotate in his grave. No, let's forget about it. So E squared is the thing to concentrate on. And so if E depends on time, that's possible to understand. And now let me discuss this from a particular point of view. Let me assume that the standard model is embedded in a group like SU5 or SO10. SO10 in particular I would like to mention, because SU5 by now is excluded. SO10 is not excluded. SO10 was introduced by me and by Peter Minkowski already in 1975, and it seems to be a nice group. It's now taken up by the string people. And in SO10, all the fundamental particles are in a 16-dimensional representation. You have electrons and you have electrons and positons, of course, but also neutrinos and antineutrinos. And that means neutrinos have a mass. which can also be easily understood in SO10. So so if you look at SO10, what happens is the coupling constants converge at high energies and give a so-called grand unification. Now the question is, if you have a grand unification, how can you get a time dependence of alpha? Well, you can introduce it by making a change of the unification energy or even a change of the coupling constant at high energies. There are two ways of doing it. But in both cases, you see, you get a change of alpha, but also of alpha strong. And so alpha lambda will depend on time. And we did a calculation here based actually on a particular model, which particularly is simple, SU5, but not the normal SU5, which right now is excluded by experiment, but by the so-called supersymmetric SU5, where you have supersymmetry coming in. I don't believe in supersymmetry necessarily, but let me just take this as an example. And then they combine here. In SO10, you have a similar convergence. Doesn't make too much difference. And then we make a change of the coupling constant. And we get an equation which was also derived at the same time by Langacker and collaborators, Segre, and by me and a graduate student, Karl May. And this is the relation. A change of alpha and change of alpha strong are related, and related also to the change of unification energy. If the change of unification energy is 0, you have a change of alpha and alpha strong, as you see here, rather simple. The number 8/3 is just coming from the fundamental charges. And from that you can calculate the change of lambda. And the change of lambda turns out to be 40, about 40, 38.8, times alpha dot over alpha. Suppose that relation would be correct, it would mean, for example, that magnetic moments of nuclei would have a change here. And this can be tested by experiment, and we'll discuss the experiment in a few minutes. And if you change the unification energy and keep the coupling constant invariant, you get a similar relation, except with the opposite sign. The sign can easily be understood, actually. So it's an opposite sign effect. But again, a rather big change of lambda. And the question is then, can we understand it? First of all, I should say, this change of lambda would also get away from that Oklo constraint. But in Oklo, if you change lambda just as well, then there are cancelling effects, and the constraint goes out of the window. And then, let me now make a comparison. And actually, I discussed this with Mr. Hensch, who is a leading quantum optics guy in Munich. And so I got this idea, and which is now being checked right now. Let me look at a cesium clock. Cesium clock are the clocks which determine time at the present, at our time here. And in Munich, it's the only place in the world where you have something which could be called a hydrogen clock. Why a hydrogen clock? Mr. Hensch has a big apparatus here measuring the atomic transitions of hydrogen with very high precision. And he can do it so well that he can even use it as a clock. He doesn't like when I talk about the hydrogen clock, but Hensch isn't here, so I could mention it. And then I compared a cesium clock with a hydrogen clock. In hydrogen, you have normal atomic transitions. In cesium, however, you have a hyperfine transition. It's a nucleus coming in. And if the nucleus changes because of a change of alpha strong, then you have a bigger change here than here. And the difference is about 3 cesium cycles per day. It's not a very big effect, of course. And I mentioned this to Hensch, and Hensch looked at me and said, look, I could measure that. And so they started an experiment at the MPQ in Munich. At the same time, in Boulder, Colorado, at the IST, they did the same experiment, because the people in Boulder always do what Hensch is doing. They first look at what Hensch is doing, and then they copy it. And Hensch is sort of the guy, the leading guy in the field. And Hensch and also Mr. Walter in Munich, then looking at this from this point of view, let me suppose, this is very hard to read here, but it doesn't have, here you can do a little bit better. if a change of alpha is as big as as the astrophysics people say, namely minus 1.2 times 10 minus 15, it's measured to be minus, and the change of lambda is something like a factor of 2.4 times 10 minus 14, just as an example. That would mean a factor of, let's say, 20. I didn't really take 30 as I was calculating before, but it's just as well. Doesn't really matter. And at Cesium Clock, you define the second by so and so many cycles of microwave light. And now the hyperfine transition in the cesium is given by ME over lambda, lambda QCD lambda, times alpha to the fourth. And so a cesium clock and a hydrogen clock have a different dependence, as I was saying before. And so what you could do is first do an experiment comparing cesium with hydrogen. And this I will discuss in a few seconds or minutes. And the secondly, Mr. Walter in Munich is now trying to prepare another experiment comparing trapped indium with trapped silver. And he claims he could be sensitive up to something like 10 to the minus 17. And this is wrong. It's not 10 to the minus 14, but 10 to the minus 17. So he could measure a change of lambda something like up to 1%, like 2 times 10 to the minus 14, up to 1% as an example. But this will take 2 or 3 years still to do. But the experiment right now in Munich is the following, and also at the ISD in Boulder. So look at the optical frequency of hydrogen relative to the cesium atomic clock. Use a 486 nanometer dye laser in the hydrogen spectrometer, and take as a reference not a normal cesium clock, but a special cesium clock which was brought in from Paris, from the LPTF Paris. And actually that clock was supposed to fly on a satellite. And Hensch called up the director of the institute and said, look, I need this right away. He gave reasons. And the director decided to get rid of the satellite experiment for the time being. And they sent the clock again to Munich. It was already in Munich 1999. In 1999, Hensch had already measured the thing rather precisely without having a reason to do it. He just measured it. But now he could compare it to a previous experiment. And he used his special complicated apparatus, which I don't want to mention in detail now. But I mentioned just here the 1s2s transition of hydrogen is now measured with this very high precision, you see, whatever hertz it is, plus minus 18 hertz, very, very high precision, incredible precision. And this is the result which Hensch is getting. This is the change of alpha. He can make a statement about alpha, but in particular of the magnetic moment. 0.6 times 10 to the minus 14 with a rather small error. If you compare it with other measurements, again with other experiments, the results are even slightly better. Mu dot over mu is 2.4 plus with an error of 6.8, rather big error still, times 10 to the minus 15 per year. Now, what I was intended is measured, published in Fritzsch Letters recently, last year actually. In the simple model, I was expecting, I discussed it before in the grand unification, I expect a change of mu of the order of 2 times 10 to the minus 14. And you see, comparing this with the other limit, it's basically excluded. Not to a high degree excluded, but also well excluded. And the question is then, what do we do? Well, it was recently in a paper by John Schwartz and Ed Witten, it was pointed out, I looked also at the thing, that in superstring theory, you get such time changes of alpha and also of alpha strong. However, what happens there is usually at the same time a change of the coupling constant and of the unification energy. Both things come together. And if you have both, I was saying before, you have opposite signs, and because of the opposite sign, you can have a partial cancellation, which is suggested by superstring theory. And so you can easily have a situation where lambda dot over lambda is not 30 or 40 times alpha dot over alpha, as I was saying before. This is also extreme case, but something like only 3 or 4 times alpha dot over alpha, the same order, slightly bigger maybe. And now it turns out Mr. Hensch is now doing still the experiment in Munich. It's still going on. It seems to see, he seems to see an effect right now. It's not yet published. And maybe I shouldn't talk too much about it. But if he finds it, would be a rather interesting discovery. And the effect he seems to find is between 4 and 5 times 10 to the minus 15 per year. So it's a factor of 2 to 3 compared to that. That seems to be not such a bad thing to have. But we have to see whether that thing holds up. And in Boulder, Colorado, you are doing the same thing. So, and that's about it I wanted to say about the time dependence of the coupling constant. It's still not completely clear. It is clear that the basic relations which we would get from very simple grand unification models, that's by now excluded, but there could be this partial cancellation. Again, the summary now. We have these 18 constants in the standard model, or even more if you have neutrinos. We could have possible relations among them, so the basic number of constants is going down, but still we have quite a lot. Grand unification relates alpha weak, alpha strong, and alpha. We might have a time dependence of alpha. I should say that the experiment I mentioned by Mr. Wolf and Webb is challenged by other people. There is another experiment by Reimers in Hamburg. Here he looked at a quasar, only one quasar. He couldn't find an effect. But his errors are still rather large, so it's not so clear. There is another experiment in Paris, which also doesn't seem to see anything. But there will be another experiment going on in the States, again at the Keck telescope in Hawaii, and that might settle the thing. For the time being, I was assuming this astrophysical value as an example. If you have a time dependence of alpha, we also would have a time dependence of alpha strong and alpha weak. Alpha weak is very hard to measure. I didn't even mention that, but alpha strong you can easily measure. The Oklo constraint gives this constraint is between the time dependence of alpha, but it's very questionable, and I gave the reason for that. And typically I expect in grand unification models lambda dot over lambda is something like 30 or 40 times alpha dot over alpha, which would imply a rather big change in Cesium clock, which is not given by the present experiment. The naive expectation does not come out. The effect seems to be there, however, but 5 or 6 times smaller. We still don't know where the effect is really coming from. It could well be such a cancellation as expected, for example, in superstring theory. And this is my last transparency. Let me just go back here. This is a picture of the inflationary universe. The last picture of the Discovery magazine when it was closed down 3 or 4 years ago. But it shows how the mechanism goes in the inflationary universe. And the birth of the fundamental constants, at least many of them at least, are probably created artificially by the Big Bang. And that means if you would repeat the Big Bang, you will get different constants, maybe also different time dependence. But in any case, presumably in science, we will not have a way of getting any more information about these fundamental constants except measuring them and keeping them as our solid numbers for measuring things. But we probably have no way of finding out in detail. There will probably never in the future be a calculation of alpha and things like that. And here is a different Big Bang, probably with different constants, many, many of them. So that's the picture I have, and let me close with that. Thanks a lot.
Thank you very much, Harald. Very challenging situation. We have time for some questions.
Carolina has one.
Just 2 comments. One is that probably the most ingenious explanation for the value of alpha was made in Israel by the late Gershom Scholem, who noticed that 137 is the value in the Jewish mysticism, in Batra, of the word Kabbalah.
Yeah, I learned this once from Weisskopf, but unfortunately the most basic number is now 127 from lab. The 137 should not be taken so seriously.
The second comment is that probably the first person to study dimensionless numbers was equally probably successful as some of the group theoretical constructions you mentioned was Kepler, who was studying the ratio of radii of planet orbits. And he had the ingenious theory that they correspond to perfect solids enclosing one another.
Again, a wrong thing. You were ahead again. Take a microphone, I don't understand.
Hitler wrote a letter to the editor to make sure the publishing, they said to the editor, we take a crystal in room temperature, freeze it down to absolute zero. We have 273 degrees. Add 1 degree of freedom for the rotation of the entire body. Divide by 2 because of the electrons, two chiralities. And you have, this is 137. This is the number that Professor Eddington is trying to calculate. Published by nature. The editor doesn't see the editor was very, very angry about it.
Eddington also had an interesting explanation. He compared it to 136. And 136 I got out of a number of charged particles counting in this funny way. And then he said the experimentalist should find 136. He should remeasure 137 is not correct, which of course is crazy.
No, maybe the rest is just a perturbation.
Yeah, but Eddington gave up at that point. You see, no?
I was under the impression that Dyson, there was a period when people thought alpha was changing and Dyson was bringing this Oklo thing. And I thought it had to do with rhenium or something, some situation where there was a beta transition of like 3 electron volts. I just totally breaking up. Was something like this? Because the alpha change will affect more isostates between like, NP mass and even different.
Yeah, but this I don't know. I have no idea about this.
Because the alpha strong change will affect it less.
I know that Dyson doesn't like a time change of alpha. This I know. And so for that reason he concentrated on the Oklo thing, made it very precise. But you have to see.
If indeed one finds time dependence of alpha, I don't see any way to reconcile this with general covariance other than introducing a field, a scalar field. I mean, you cannot just plug in an alpha field in the action. So I wonder, in that case, this phenomenon should be accompanied by other, like violations of the equivalence principle, modifications of Newton's law, and all that.
Yeah, but in
so I think one should look at correlations between. In fact, these correlations do exist in specific models where there is variation.
yeah, but I'm a bit skeptic about equivalence principle and all that. For me, a change of alpha could easily be understood. But you are right, it must be related to a certain field, and that precisely happens in superstring theory. That these coupling constants are related to a scalar field.
Yeah, it's just light field, you expect a force.
Yeah, this can easily be, but it doesn't mean anything about equivalence principle. That's another story. That's too complicated somehow. There's a question up here.
Throughout the talk, you were talking about the global change of alpha throughout the universe. And you didn't mention, is there a possibility of slight variations within the universe of alpha within certain areas, and they may change each time a little bit? I mean, why assume a single alpha?
No, that had a reason. I should have mentioned it. First of all, people have found the time change of alpha. That experiment, they looked also for a local change of alpha. They looked at the quasar here, in different directions, and they found for the quasars which are in a similar distance from us, in the same different directions, the same effect. It was, that is not completely understood why. There should be a small time change, a small local change, but it seems to be that time is more more an interesting parameter for alpha than space. But why that is, we don't know. It might be related to the Big Bang. Also in the Big Bang is very homogeneous, and in different directions you see the same thing. So there seems to be something there. But if the time change of alpha is established in future experiments, people would have to also look at local changes more precisely. And maybe they find an effect. But at least right now it seems to be, if the effect is there, the local change is less, at least a factor of 10 less than the other change. Probably related to the Big Bang.
Harald, we keep talking about alpha. Maybe we should try to measure the electron mass or the muon mass.
Oh, people, muon mass you cannot measure with such a high precision. But the electron mass also has been measured by the laser people. And there, of course, you don't see a change either. The real trouble might come if the electron mass, if alpha in the nucleon mass, if all three change in time, then we really have a mess, because there could be cancellations, there will be cancellations to some extent, and then it's very, very complicated. So one should keep that in mind. And Hensch is in fact looking at it, the electron mass. They have special experiments in Munich, also to check this. But for the time being, he concentrated on the value of mu, of the magnetic moment.
Yuval.
I have a true story. I used to like science fiction very much. And there was a series, I remember the story Beyond the Blue Eye, I think a series by Paul Anderson. And in the year million, the man writes that he finds a document saying that there was a theory saying that the constants of nature are changing. And he's very interested in that. And he explains it to a friend. He can say the role in the story. And he says, take for instance pi. Here it is 3.14, but elsewhere it might be 7. So I wrote a letter to Paul Anderson to explain to him that constants of nature, if pi is a mathematical constant, pi is pi, whatever you have. And it's not this. He promised that in a future book he'll explain more about the he will correct.
Incidentally, when we really talk about it, we don't really know which will be the rate of change theoretically. Bergstrom and myself have proven that nucleosynthesis time would have not been different from a few percent of it today. Otherwise, the lithium production would not.
Yeah.
So we know that the change is until very early in the day, but we don't know how and when they occur. Many string models, of course, very early.
But in the present experiment, it's also a very small change, 10 to minus 5.
No, nothing.
So there's nothing wrong with that.
Any other question? If not, we thank Harald very much.